President Bloom, members of the Xanthos family, friends and colleagues, ladies and gentlemen, thank you for joining us today for the 2016 Marino Xanthos Memorial Lecture. The lecture was organized by family and friends of the late Marino Xanthos, who passed away in summer 2013. By that time, Professor Xanthos has served at NJIT for 18 years, having worked earlier at Martin Marietta Resources International and at the Stevens Institute of Technology. Among his positions here at NJIT, and in addition to his role as Professor of Chemical Engineering, he was Director of the Polymer Engineering Center, Director of the Center of Processing of Plastic Packaging, Chairperson of the Executive Committee of the Materials Research Council, Senior Technical Advisor to the Polymer Processing Institute at NJIT, and Associate Professor for Graduate Studies. Professor Xanthos was an internationally recognized expert and researcher in the fields of reactive polymer processing, polymer extrusion foaming, and polymer nanocomposites. He was also a strong advocate of plastic sustainability issues. One of his last papers, and one which I hear he was very proud of, was published in August 2012 in the special issue of Science devoted to working with waste. The title of this issue shows a photograph of bales of compressed aluminum cans destined for recycling. The Marino Xanthos article in this issue is titled Recycling the Number 5 Polymer. It deals with recycling of polypropylene, PP, and I'm showing you here a figure from this Science article. PP is a thermoplastic polymer used in a wide variety of applications, including packaging and labeling, textiles, applications such as ropes, thermal underwear and carpets, stationary plastic parts and reusable containers, laboratory equipment, loudspeakers, automotive components, and polymer banknotes. The article discussed the factors contributing to PP recycling rates, which include collection and separation efficiency, processing chemistry, and market dynamics for the products derived from recyclates. Let me mention the two publications of Marino Xanthos which have garnered the highest number of citations from among his many studies. Here is an image of the cover of a book he edited and published in 1992, Reactive Extrusion, Principles and Practice. It has by now been quoted close to 400 times. A second book, Functional Fillers for Plastics, was published by Wiley and had a second edition in 2009. About half of it was written by Professor Xanthos, and it has been cited in the literature close to 300 times so far. Today's lecture follows a technical session in memory of Professor Xanthos. It was held at the 2014 Society of Plastics Engineer Annual Technical Conference on April 2014 in Las Vegas. In 2015, a memorial lecture was held at NJIT, which was given by Professor Morton Den of the Benjamin Levitch Institute at City College of New York. It is the intent and plan of NJIT to organize and present this lecture on areas close to the professional focus of Professor Xanthos in perpetuity, and I'm pleased to acknowledge the work of the committee in charge of this task, which was chaired by Professor Piero Armenante, and whose members are our colleague Lisa Axe, Cheryl Baker, Roslyn Manning, Kamalesh Sirkar, Trevor Tyson, and Cynthia Woss. We are also very pleased that we have with us today Dr. Joel Bloom, the president of NJIT, and I invite him at this time to come forward for welcoming remarks.
Good afternoon, and welcome to NJIT, particularly the family and friends of Marino Xanthos. In order to add to the legend of Marino, and not necessarily focus on his outstanding academic accomplishments, I'll describe some of the work that I had the opportunity to engage Marino in my former job here as a vice president. As the associate provost for graduate studies. We were still, even when Marino comes into the position, a fledgling university putting together graduate studies, the research attendant to graduate studies, the recruiting of PhD and master's students. And Marino brought a very fresh perspective to doing that from his predecessor. In fact, he advocated strenuously for full funding of our PhD students, as well as funding for master's degree students. He also was very concerned about the differentiation between a TA and an RA and how we would move those students along that continuum where they would be able to complete whether it was a master's or a PhD in a timely fashion. And you could ask him to appear anywhere at any time to address some of our undergraduates, particularly at that time those in the Honors College, who were very interested in continuing their MS or their PhD work here. And as the Honors College continues to grow and develop, I do have a particularly vested interest in it. We see more and more of our MS and our PhD students coming from the Honors College and following the pathways that Marino laid down to ensure that they can easily transition while undergraduates into graduate work, into funded graduate work, and from an MS or from a BS right into a PhD. So a lot of what is occurring here with the growth in research and the growth in PhD students was as a result of the work that Marino did while he was our Associate Provost for Graduate Studies. So it is my pleasure to recall his work, to thank his family, thank his son who's here today, for giving to us some of his very, very valuable time. And this lecture series. The lecture series is supported by the family, by many of you in this room, friends of Marino's, and even some former graduate studies. And it was established particularly to pick up and continue the work that Professor Xanthos, our research faculty member, did prior to coming here and continued while he was here. And it's through that generosity that we welcome Professor Thomas Russell. He is the Silvio Conte Distinguished Professor in the Polymer Science and Engineering Department of the University of Massachusetts at Amherst, as well as a visiting professor at the Lawrence Berkeley National Laboratory and principal investigator at the Advanced Institute of Materials Research at Tohoku University, Japan. Professor Russell has co-authored more than 700 peer-reviewed publications and more than 20 books and book chapters, and his name appears on 11 patents. Congratulations. Today, Dr. Russell will lecture on breaking Moore's law. I'm sorry I can't stay here to hear it.
I wish to invite Dr. Harry Xanthos, Professor Marino Xanthos' son, to speak on behalf of the family.
So thank you, Dr. Kam. As Dr. Kam said, my name is Harry Xanthos. I'm one of Marino's two sons. And I'm just going to be brief, but I just wanted to, on the behalf of the family, just to extend my gratitude and appreciation to NJIT, as well as and particularly Dr. Kam and Dr. Armenante for setting this program up this year. Additionally, I would also like to extend my appreciation to Dr. Russell for kindly accepting to take part in this program and for presenting on a topic that is very much aligned to my late father's work and areas of research. So my father, many of you may have known him, served the academic community for many years and was passionate about education, research, and mentorship, and had the opportunity to make a huge impact on a lot of students' lives as well as his peers. As such, I'm very happy to see his legacy at the university to be carried forward and celebrated in the form of this lecture series. So thank you very much again.
Thank you, Dr. Xanthos. Today's speaker and lecturer will be presented by Dr. Piero Armenante. Dr. Armenante is a distinguished professor of chemical engineering at NJIT, and he also serves as director of the NJIT graduate program in pharmaceutical engineering. He is the chair of the Marino Xanthos Memorial Lecture Committee.
Okay. So, good day, everyone, and Kam, colleagues, students, and especially friends and family of the Marino Xanthos family group. Today, I really have a distinct honors and privilege to introduce today's speaker, Professor Thomas Russell, that was announced before, of University of Massachusetts at Amherst. However, before introducing Professor Russell, let me just spend a couple of words remembering Marino. Marino was not just a colleague of mine here in CBP, my department, chemical, biological, and pharmaceutical engineering department, but also a person that I really remember with great fondness because of the close personal relationship that I had with him. So I worked with him for actually quite some time because he was not only a scholar, and you already heard some of his accomplishments, but he also took a great pride in his students. So he, in fact, advised, as a PhD student, one of my former master's students in the pharmaceutical engineering program, and was very, very good. And in fact, I remember learning, well, a bunch of us learned about what happened to Marino from this student, from Non-Charles, Dr. Non-Charles Choncharn. And because of his expertise, I mean Marino's expertise in material sciences, and the fact that we in this department develop a number of programs related to pharmaceutical engineering, Marino and I actually put together a full-blown program at the master's level entitled Master's Science Program in Pharmaceutical Materials Processing. And we completed the entire process, including approval at the state level. And the program is now practically on the book, but was never launched because you know what happened when Marino early departure. So it is with the spirit that I'm very pleased to have the honor to chair the committee that now celebrates or commemorates Marino's life. So I very pleased in this respect to have such a distinguished scholar giving us the second lecture of this series of lectures that we hope will extend for a long time, named after Marino. Now, I could go, and I will to a certain extent, go through Professor Russell's vita, but if I do the whole thing, it would probably take us a few hours. So I have just a condensed version of his accomplishments. So as was already mentioned by the president, Professor Russell is the Silvio O Conte Distinguished Professor in the Polymer Science and Engineering Department at the University of Massachusetts at Amherst, as well as a visiting professor at the Lawrence Berkeley National Lab and a principal investigator at the Advanced Institute of Material Research at Tohoku University in Japan. He started his academic career in 1976 at Boston State College, and at lunch we had an interesting discussion about his earlier background. And there he received his bachelor's in chemistry. Then he went on to receive his MS degree and PhD from the University of Massachusetts at Amherst, so full circle. Now he's back there and has been there for quite a while. But after he completed his studies, he moved to Germany, and he worked there as a research fellow at the Institute for Physikalische Chemie, Universität Mainz. And then after that, he moved back to the US at the IBM Almaden Research Center as a research staff member. And he stayed there for 16 years, so he acquired also a significant industrial experience that I'm sure was and is very useful in his academic career. Then in 1996, he returned back to academia, again as a full professor at the University of Massachusetts at Amherst, where he is today. So Professor Russell's research interests are focused on the science of soft matter, including surface and interfacial properties of polymers, phase transition polymers, directed self-assembly processes, and the interfacial assembly of nanoparticles, wrinkling and behavior of thin film polymers, and the structure and morphology of polymer-based photovoltaic materials. In a way, the President already stole my thunder, but just let me mention again that he has an impressive list of accomplishments. He has more than 700 peer-reviewed publications, more than 20 books, 11 patents, staggering 45,000 citations. His H index, if you know what I mean, is 111, if I'm correct, unless it went up since yesterday. So he has received a number of awards, delivered more than 500 invited keynote, plenary, and name lectures, addresses around the world, lectures. He's a member of the American Chemical Society for Applied Polymer Science, and he received the award from that society. He also received the Fred Cleverly Distinguished Lecture at Material Research Society, the Polymer Physics Prize for the American Physical Society, the Otto Work Prize, and the Dutch Polymer Award Prize. So I'm only mentioning a few of them because the list is extremely long. And he's the Associate Editor for Micromolecules. And he's, last but not least, an elected member of the National Academy of Engineering. So as I said, this is just a short, abridged version of Professor Russell's accomplishment. And at this point, I think I spoke enough, and I think it would be time for me now to give the podium to Professor Russell. So please join me in welcoming Professor Russell.
First, it's an honor to be able to make this presentation in honor of Marino Xanthos. It was an honor to be selected to give this presentation. I thank the committee for being selected and for the invitation to present some of our work. So, before the presentation, I was speaking to Jenny, Marino's former wife, and I said that she told me I had to make this simple so that even her son could understand this. And I said, don't worry, I'll ask Curtis a couple of questions. And if Curtis can't answer the questions, then Piero will have to, so which is fine. So what I'd like to do today is to present some work that's been going on in my laboratories for some time. And it's work that eventually is getting to the point where we are breaking what's called Moore's Law, and I'll describe what Moore's Law is in a minute. The work is done by a series of graduate students and postdoctoral fellows, and I'll touch on some work that was done with Javid Razayev, who is currently at the he's at the University of Buffalo in the chemistry department. The work is supported by the Department of Energy, National Science Foundation, and in part by the Seagate Laboratories. Now, this is a slide, I have to admit, I took most of the information from the internet about Marino Xanthos, but he is a recognized expert in the area of reactive polymer processing, and I think I may touch on that in my presentation. I'll also, I won't discuss extrusion or foaming. I am not working in extrusion or foaming at all. In terms of nanocomposites, yes, I'll discuss that as well. And I wasn't cognizant of the fact that he was very much interested in plastics to sustainability, but that actually is a current interest of mine. Not in terms of that, when I first saw that photograph that you showed of all those cars that were stacked one on top of the other, you can get a photograph that looks exactly like that for plastics in the ocean, all right? So that plastics are a very important contributor to pollution, and it's something that we as polymer scientists must be very cognizant of. So, This is Moore's Law. I worked at IBM for 16 years. And Moore's Law says that the areal density of elements has to increase by a factor of 2 every decade. And it says that if you have to follow along this little red line, and I extrapolated that to the present, and if the companies don't meet that requirement, they'll fail. Now, Moore's Law is not a law. It's just an extrapolation in terms of performance. But it's something that Wall Street looks at that, and that's what they're expecting to get from the different companies. And right now, industry has a problem. Industry has done remarkable with photolithography, whereby you can take light, be able to expose a film, all right, that basically is a photoresist, where I can imprint a pattern on the surface. And currently now the industry can get down to roughly about a 14 nanometer half pitch. Now a 14 nanometer half pitch, a pitch is going to be, if you have a periodic structure, it would be half that pitch. So they can get down to now a full pitch of 28 nanometers. 28 nanometers using light. That's remarkable. Really is. You know, because the light that you're using, or it's going to be something that will have hundreds of nanometer wavelength. To get 14 nanometer resolution, where I can put things exactly where I want them, is stunning. However, industry has a problem. And the problem industry has is they use light. And light has a given wavelength. And there is going to be a hard limit. There will be a diffraction limit as to how small one can go. Curtis, what do you do then if you're running into a problem? And he says, oh, I turn to my advisors, and they'll tell me everything. So to get around this problem, it's not going to solve it forever, but to get around this problem is not to use light and to have a top-down approach, but rather to be able to use a bottom-up approach. So that if I could take molecules, and I could allow molecules to self-assemble, and I could allow these molecules to be able to form a pattern that I would like, and if I can reduce the length scale of the structures, it would be great. If I could take some of the copolymers, now a block copolymer is a molecule where I take one polymer, could be polystyrene, and I attach this to another polymer. It could be polymethacrylate, polyvinylpyridine. But polymer molecules don't like each other, all right? They don't like each other. Non-favorable interactions make these blocks separate. And they separate on a size scale that is commensurate with the size of the molecule. Typically, polymer molecules will pervade about 10 nanometers in space. So the size scale of these structures, these domains that I would get, will be commensurate with the size of the molecule, and that places us on the 10 nanometer level. All right? The molecules will self-assemble into these different types of structures by themselves, and I get that free. As long as I can get a synthetic chemist to synthesize these molecules for me, it's great. All right? I can get spheres, cylinders, gyroids, lamellae, etc. We know a lot, a tremendous amount, about how these molecules phase separate in the bulk. All right? The question is, if you think of it, the number of applications that have emerged from these molecules has not been huge. There's been some. However, if I can take these molecules and I can make them in thin films, and if I can control the orientation of the molecules, and if I can control the lateral ordering of these molecules, there are some very unique applications that will emerge. And in fact, if I can learn to control the size scale of the structures, and if I can get structures where I would have a full pitch of 4 or 2 nanometers, it's awfully small, then I would basically take myself and I would place myself orders of magnitude above Moore's law. And I think we can do that very easily, and we're close to being able to do that now. The trick is we need to be able to control how these domains, let's say we had cylinders, how these cylinders are oriented in the film, whether they're parallel to a surface or they stand vertically. Because if I can control the orientation of these structures, and if I can control the overall lateral ordering, the types of applications are going to be immense. And this just shows you a couple. So this happens to be a block copolymer where I have all cylinders standing vertically, and I've removed the cylinders. So now I have holes. So this basically is a membrane, polystyrene matrix with holes. The holes in these are commensurate with the size of these domains, and in this particular case, it's 15 nanometers. So here I have a polymer film that has 15 nanometer holes that are separated center to center by about 30 nanometers. It's really a high areal density of holes. You can use that as a filter, and I can filter viruses with this. I can filter virus particles which have size scales that are 10, 15, 20 nanometer, and I can use this as a separations media. Alternatively, I can take this, and this is the film happens to be on a silicon substrate, and I can use an ion beam to etch into the underlying substrate. Substrate is silicon. It's a semi-conductor. I let an oxide grow back, and I can evaporate a metal on the surface of that, and I have a capacitor. It's very simple. No lateral order in this particular case whatsoever. I'm just using the copolymer as a template to be able to transfer this pattern to the underlying substrate. I could use it as a scaffold where I can grow materials. So I have this template on the surface, and I can do surface chemistries to be able to grow structures from a surface. They could be pillars. And you may say, who cares about growing pillars from a surface? Well, if I can give you a surface where I can grow pillars, I can increase the surface area. And if I can increase the surface area, and if you're interested in sensors, I can increase the sensitivity of a device by the amount of increase in the surface area. We also had used this with a thicker film to be able to grow nanowires. And the reason why nanowires are important is that if I can grow, say, chromium in these templates, then I can give you a material that is magnetic, and I can use this as a magnetic storage type of device. You can also build other types of devices, etc. Now, here we have a polymer film. And I want to be able to control how these domains are oriented, whether they're oriented parallel or normal to a surface. Now, I worked at IBM for 16 years. If I give you something that's hard to do, that requires multiple steps, industry will say, adios, go home. Whatever I do, it has to be really easy to do. It has to be something that's reliable, so that the first time I do it is the same as the second, third, fourth, and fifth, and sixth. It has to be something, if I want to use this on a production line, it has to be fast. Can't take me days to do it. It also has to be such that if I'm going to use this to transfer patterns, the contrast between the components has to be high. You know, it has to be black and white, so I can easily take the structure and transfer it. And I mentioned already about the orientation and the lateral order. And you know, industry has already told us, we can do 14 nanometers as a half pitch. If you can't do better than that, don't bother. What's the point? All right, we can already do this, and we can do it quite well. So, if I consider a simple polymer, oh, Piero, please. I will, huh?
Do I have to stand up?
Yes.
Like a show here?
No.
Okay, good.
Move over a little bit. Good. Is he always this difficult in class? So I am a white block, and he is a blue block. All right? So I'm a polymer chain. He's a polymer chain. You know?
And we are holding hands.
And we are chemically bonded together. That's correct. So what dictates size scales of structures? How big we both are. So the molecular weight is important. The bigger you are, and the bigger I am, the bigger the sizes. And the smaller we are, the smaller the size. But the problem is that when we get too small, then what happens is we start to mix.
Uh-oh.
No, don't go. No, don't go this way. It's true. Let's see, what else is there? Oh, are you ready? So, just step back.
Yeah.
There. So, I happen to be a polymethylmethacrylate domain, and he happens to be polystyrene. Okay. So, the first row of chairs here is silicon substrate. First row of chairs, silicon substrate grows in oxide. I am polar, you aren't. And so that means if I were to take a film, spin coat it, then what I do is I go automatically to the surface. We're connected, so where he goes is dictated by where I go, just because of the connection. And if this happened to be an apolar surface, then we'd do the other way. And if it happened to be a surface where the interactions were balanced, then we both go down. Now, I just showed you something really simple. By controlling interfacial interactions, I can control the orientation of materials at the surface. Trivial to do. I can take a surface and treat it beforehand, before production, etc., spin coat a film, heat it above the glass transition temperature, things move around, and I can control the orientation. I can also help controlling the orientation by controlling the thickness of the film. Because if the film happens to be commensurate with our size, then I put no frustrating forces on the film. But if the film happens to be a little bit thinner, it gets a little bit, we start to get squeezed. And so that helps me in terms of controlling the orientation. Thank you very much. Could I have a hand for my assistant? Now sit down. You're not going to get any more. That's it. You're just let's get ourselves together. So, interactions between the two of us, size, and then interactions with the substrate. Those are basically the parameters that are dictating where things are going. However, polymer molecules, unlike small molecules, are big. And since polymer molecules are big, they tend to diffuse slowly. And if you want to think of an application, that's what you don't want to have. You want to have things move rapidly. So to do this, to get around this, the way you can, don't you fall asleep yet. You can't fall asleep. I'm going to catch you. Jenny was there, yawning away. You're not going to get away with that, young lady. So, you have to induce mobility in the film. And the way you induce the mobility in the film is you want to take the glass transition temperature and drop it. And the way you drop the glass transition temperature is you can use a solvent. And if I use a solvent, I can speed the processes up. Alternatively, I can say, all right, we have a glass transition temperature, and we heat above the glass transition temperature to get things to move around. But I'm going to show you some experiments that we have done where we're trying to use effectively solvent. So if I take a film, this happens to be polystyrene, polyvinylpyridine, it doesn't matter. Red molecules, blue molecules, it doesn't matter. And I spin coat a film of this, there are cylindrical microdomains of polyvinylpyridine. And if I spin coat a film, what happens is that interfacial interactions will be balanced by the presence of a solvent as well as the interactions of the materials with the substrate. And I get these cylinders standing normal to a surface. The cylinders here are on the order of about 15 nanometers. There's no lateral order, and in fact, if you look at the structures, they're rather irregular. I take this film and I put it in a solvent. It happens to be tetrahydrofuran. It's just a solvent that's a good solvent for polystyrene and a good solvent for polyphenylpyridine. And I just put it in the vapor. And in this particular case, I left it for an hour or 4 hours, but you can make this go much more rapidly. And what you find happening is that these little cylindrical domains start to get much better defined, and we start to get very high order in the film. It's trivial. Take a film, spin coat it. Spin coating is done every day in industry. Throw it into a solvent vapor. Solvent vapor imparts mobility. Non-favorable interactions between the components wants to reduce the number of defects in the system. And in fact, you start generating these structures where you see this beautiful hexagonal array of cylinders. It's really nice. And in this particular case, the question is that can we take these films and can we control the ordering, the lateral ordering? Because if I could put and address each and every one of those elements, if I could sit on a cylinder here and go over a certain amount to another side and tell you whether I'm on a cylinder or not, that means I can address it. And if I can address it, that's storage. It's magnetic memory, because I can replace the polyvinyl 4-vinyl pyridine with a material that's magnetic. And that's, if you think of the magnetic heads, that's exactly what's happening, is that we're reading a magnetic element, we're writing a magnetic component, we're reading it, and what's important is that we have to know where we are in this particular substrate in order to address it. If we can do what I think we can do with copolymers, current storage devices will have to change, and we'll have to go with devices that are all solid state where there are no moving parts. But that's the subject of a different lecture. Now, certain people have heard a lot about nanotechnology. And with nanotechnology, the size scale of the structures are, how big are they?
14 nanometers.
No, not 14. That's nanometers in size. That's okay. Now, I want you to think of this. Typically, substrates may be, let's say they're an inch, 2-inch diameter, maybe more. And the elements that I have on the surface are nanometer in size. How can I characterize structures on the nanoscopic level over macroscopic distances? That's really hard to do. And the reason is that these elements are so small, I can take in a scanning probe microscope and I can look at a micron by micron area. All right? Now, if I have a substrate that happens to be 2-inch in diameter, all right, how many microns is that? That's a whole bunch of microns. It'll take you forever to characterize it. So you need to have a technique that can characterize things over a large area on the nanoscopic level. When you think of nanoscopic level, you can think of scanning probe microscopy, or you can think of X-rays. Now, X-rays are great because they can characterize structures on the atomic level or the tens of nanometer level fairly straightforwardly. X-rays have a wavelength that may be 1.5 angstroms, a tenth of a nanometer, so it's commensurate with the size scale of the structures. But in order to probe a large area, we used what's called grazing incidence X-ray scattering. Now, what grazing incidence X-ray scattering is we take an X-ray beam and we bounce it off a surface. So if you think of taking an X-ray beam that may be 3 micron in diameter, bouncing off a surface at a grazing angle, then we project the X-ray beam over a large area on the surface. And we can probe areas that are roughly about 1 inch in length with the X-ray beam. So we can characterize structures over large areas on the nanoscopic level. It's not perfect. I can't tell you if I have 1 defect or 2 defects or 10 or exactly where the defects are, but I do get an average measure of the overall ordering in the material. From the spatial position of the reflections, think if I have cylinders standing normal to a surface, what that's telling me is I have an interference arising from the center to center to center distance between these domains. So I see a peak or multiple peaks depending upon the overall order in the material. So it's very easy means by which I can tell you how big the structures are, what their separation distance is, and how well the ordering is in these particular materials. And the experiments that we've been doing is that we've been using solvent annealing, and we're trying to characterize these structures in situ real time so we can watch the development of these structures. So this is what the grazing incident scattering looks like, is that you have the central, this is the beam from a synchrotron bouncing off a surface. And what we see are these reflections, which are characteristic of the average separation distance. And I can do a line scan across, so I can look at the intensity as a function of the scattering vector, which is the angle, if you will. So it's a classic scattering type of experiment as a function of time as solvent is being annealed. And what you see is that you see this very diffuse reflection shifts into smaller angles. And the reason it shifts into smaller angles is that the size of the structures are getting bigger. You spin coat a film, you put it into a non-equilibrium state, you introduce a solvent, and then with the introduction of solvent, the molecules can sort of start to separate. And Curtis, come. I can't believe these people will do this, but you know, there's a sucker born every minute. So, Curtis, do you like me? He's looking at me now saying, I don't like you at all. And he's right. And so Curtis tries to get as far away from me as possible. You spin coat a film and you start off with things sort of a gamish. You get this very diffuse reflection. And then we introduce a solvent and then we separate because Curtis hates me. And he's really going to hate me by the end of the day. Don't worry. But you know something? I don't care. You're fired. Sit. And so what happens is that these copolymers, they begin to phase separate. The phase separation improves when you introduce a solvent because I've given the system mobility. And in fact, what happens is that you can monitor now the position of the reflection and this characteristic of the domain size. And that's given by the red. We start off initially, spin-coated film, non-equilibrium structure, introduce solvent, the spacing gets bigger, and then something curious happens. The spacing starts to decrease. And the reason the spacing starts to decrease is that the system initially stretches, and then we continually add solvent into the system. And as we add the solvent, you know, Curtis, you're bad, but you know, the solvent is between us, so it's not as bad as I thought. And so what happens is that the period begins to decrease, and we come together a little bit. All right, not too much, Curtis. What also finds is that if you look at the full width at half max, this reflection initially starts off as being diffuse, and then it starts to sharpen. And the reason it starts to sharpen is that the lateral ordering is becoming improved. All right, and this is a very quick measure of the overall lateral ordering. This is the overall film thickness. And if you think of it, the film thickness is exactly the amount of solvent that's being put in the film. Because as you add solvent, volume increases. If you're on a substrate, you can only get thicker, you can't get fatter, because you can't fall off the substrate. All right? So this tells us the swelling ratio, this tells us the lateral order, and this tells us something about the peak position. And then you basically can go through and you can do an experiment where we look at the domain size, decrease, and then if we have a problem. The problem that we have is that I can give you a film that has superb lateral order, close to being addressable. However, that's a film where I have solvent present, where I have this excess volume associated with the solvent, and the film is effectively above its glass transition temperature because I introduced the solvent to drop the TJ. Now, I gotta get the solvent out. And how I get the solvent out is very important because I have several options. One, I could take it out really fast. And if I take it out really fast, that's bad English. Really rapidly. It's an adverb. So if I take it out very rapidly, I can freeze in the structure that I have in the swollen state. Or I can try and ease the solvent out of the film to allow the film to stay in equilibrium and do it slowly. And it makes a big difference because if I take it out fast, the lateral order in the film is much better than if I take it out slowly. And the reason for that is that as I take the film out slowly, I have a problem. Now, I want you to consider these chairs as being these cylindrical domains on a surface, and the surface happens to be covered by the area covered by these chairs. And these, as Curtis showed us, initially, these chains, all right, they're sort of stretched and then they compress, and at equilibrium, we can establish a finite number of these on a surface. We have a lateral surface that has a certain area. The unit cell of these structures has a finite area. So in the swollen state, they have a certain finite number of these domains on a surface. Now we remove the solvent. If we remove it rapidly, boom, we're stuck with this. However, the situation we have is that we have a film where the density of the film is very low in comparison to what it should be at room temperature, because we've taken the solvent out very rapidly and dropped the system below its glass transition temperature. If we remove the solvent slowly, then what happens is that the less solvent, Curtis and I get to dislike each other and I want to separate. So the separation distance starts to increase. I can't fall off the side of the substrate, so I got to do something with this extra material, and I have to put it somewhere. And the only place it can go is up. No other way. And so what happens is that I'm trying to compensate now for this lateral frustration I'm putting in the film by effectively increasing the overall thickness of the film itself. And you can follow that. Well, we could follow it, but you got to believe me, folks. Just believe me again. So this happens to be a film that we swell. We get this beautiful order, and then we start to remove the film. And what you see, we remove the solvent, and what you see happening is that this reflection that's relatively sharp, as I start to decrease the amount of solvent, the film begins, this reflection begins to broaden. And the period, or the period increases because we're removing solvent. Curtis doesn't like me, so we start to stretch apart. But the full width at half max starts to increase. And that tells me that I'm importing some sort of disorder, or I'm adding disorder to the system simply by removing the solvent. What's very nice, though, is that I can remove the solvent up to a certain point, equilibrate, and then take it off rapidly, and it allows me actually to change the overall period, because that allows me to control how much Curtis doesn't like me or not, and that actually controls the period. So I actually have control, fairly fine control over the period, but even still, I have to get the solvent out of the film, and I still have a problem associated with this non-equilibrium type structure. So Jenny, are you on board still? You're not. What can I do to make your life easy? Shut up? No, I'm not going to do that. I'm going to. So, so the question is that, how do we stand? Where do we stand with respect to, we have solvent annealing. We know we can speed up the process. I know we give you an order, but I start to introduce some disorder. Well, how does this compare to, say, thermal annealing, where I don't use solvent, I just heat the material up above the glass transition temperature to impart mobility? I can define everything. I define the segmental interactions. I can define mobilities in the system. All of these in terms of diffusion, et cetera, and I can define this quite well. And I can actually do a comparison between the thermal annealing and the solvent annealing. And in the case of the thermal and solvent annealing, so this is what we saw before. We see the period will begin to increase. We start to cool, and then we get to a point where the system starts to vitrify. And it's at this particular point, when the system begins to vitrify, that we start to introduce disorder into the system. With the thermal annealing, we can do a similar type of experiment. And what we can find is that the disorder that we place in the film when it's thermally annealed is far less. But we sacrifice because it's a little bit slower. And so what this is telling me is that, yes, we can get long-range lateral order, but if we can do it by thermal means as opposed to solvent means, we're a lot better off. Now, are we perfect? I can increase the lateral order quite well. And in fact, this happens to be styrene ethylene oxide, again, red and blue. So Jenny, don't worry. You don't have to worry about what polyethylene oxide is and polyvinyl pyridine. You just think poly red and poly blue. Okay? So now what happens is that here we can change the molecular weight. And if we change the molecular weight, the size scale of the structures gets smaller. Okay? And they get smaller, and they get smaller. And in fact, we can generate these structures where we can generate a pitch with polystyrene polyvinyl pyridine of about 6 nanometers. That's 10 terabit per square inch. That translates to roughly about 30 DVDs on a quarter. And if you look at this, Jenny, do you see any defects in that sample? No, she doesn't see it. She's lying. I can see one. But that's okay. Thank you anyways. I appreciate it. No, but if you were to look at this, and if I were to ask you to find a defect in this sample, all right, you're going to be hard-pressed to find it. Spatially, it looks perfect. The student who brought this into my office, I was stunned. I said, wow, I'm going to be rich. We've solved the problem of perfecting the lateral order, right? And students usually will come into your office and they'll say, oh, professor, look at this result. And they show you a scanning probe micrograph, and it looks great. And you say to them, okay, show me what it looks like over here. And they show you what it looks like over here, and it's not the same as the beautiful little picture they brought into your office. This, however, it is independent of where you are on the surface. And this surface happens to be a reconstructed sapphire surface, which give you these very small facets on the surface. And we've used this to bias the orientation of these hexagonal arrays on the surface. If you look at that image, and if I were to do grazing incidence X-ray scattering, I could take the surface and I could rotate it. And you have a hexagonal array in 2D. You have the 1-0 planes, and you have 1-1 planes. So those are just crystallographic planes. I can rotate the surface, and I can look right down a 1-0 plane. And if I do that, I should see, as we see here, a first, a second, a third, a fourth, a fifth, a sixth, a seventh, and eighth order reflection. This is a substrate that is inches in size. I give you a hexagonal array, and I look right down the axes. I rotate it 30 degrees, and now we look down the 1-1 plane, and you see the reflections that are characteristic of the 1-1 plane. Wow. I see money rolling in. This is great. I won't have to work a day in my life after this. However, the rotational order in this is perfect. And it's perfect over very, very large length scales. Right? But there is another order parameter you have to be very concerned about if you want to develop magnetic storage. And that is, if I were to take this substrate, and if I go across the substrate, I can tell you that this rotational orientation, so I know if I go 60 degrees, 60 degrees, 60 degrees, I can look right down a 1-0 plane, or 60 and 30, 0, I can look down a 1-1 plane. However, if I go along this line, if I go from point to point to point to point to point, there's this translational order that's also important. And if there are slight fluctuations, then what will happen is that you lose order. That is to say, I can't tell you exactly whether I'm on a cylinder or a matrix if I were to start off here and go all the way down here. In fact, what happens is that you have a hexatic ordering, which is like a liquid-like ordering almost, along that one dimension. That's sufficient enough to cause this to be problematic. Now, I can tell you that these facets are running across the surface in one direction. So I can tell you that if we use these faceted surfaces, we can perfect the rotational ordering, but we need to have another means by which we can perfect the translational order. So we need to introduce some other force in this assembly process. And we haven't done this yet, but I'm going to show you what we are doing is that we're using basically a molecular architecture. And here, rather than take a simple diblock copolymer, we're taking a triblock copolymer where all of these are connected at one point, and that's called a micto-armature polymer. What's very interesting about these molecules is that they form a tiled type of structure. Now, I know many of you have tiled your patios or have tiled your bathrooms, etc. You can't place these tiles down arbitrarily, and in fact, you have to place these down in a very well-defined way. And these are theoretically what you would see for these micto-armature polymers, where you have these morphologies where you have domain 1, which is red, domain 2, which is blue, and domain 3, which is green. And we can introduce now enthalpic interactions between the components to be able to promote lateral order. And by combining these with a patterning on the surface, I'm certain that we'll be able to generate truly long-range lateral order that are perfect. How much time do I have left? I can talk to 4? I don't think people will tolerate that. Jenny says, no, you're not going on till 4. She's out of here at 4:15. All right, I'm going to show you one other. I'll finish off with this. I'm not going to discuss this. A trick. We can use interfacial interactions. We can use surface topography. When we use the molecular topology to be able to promote lateral order. But I'd like to be able to generate structures that are really, really small. We can get down to 6 nanometers. And the problem with copolymers is that there is a finite, for a given set of interactions. Curtis, come. You have to work faster. The time is ticking. So, look, Curtis and myself, we have a given molecular weight, and whether we form domains or not will be dictated by how strongly we dislike each other. All right? That's a segmental interaction. And then also molecular weight, how big we are. If I take, benzene and acetone, they hate each other. But they'll make a nice uniform mixture because entropy will win. Okay? Entropy can overcome enthalpy. So if Curtis and I are too small, enthalpy will win and we'll mix. So we can form a phase mixed structure or a phase separated structure depending upon the product of the segmental interactions and our size. And it has to be above a certain critical value. That value happens to be 10.5. How do I know? Because I know. Curtis, thank you. So, in order for me to get the smaller size scale structures, I want our interactions to be as non-favorable as possible. Oil, water, hydrophobic, hydrophilic. Pah, they hit each other. And if I can produce these structures, or such a chemical structure, then I should be able to get the size scale of these domains smaller and smaller and smaller. But there's a problem. I can prepare diblock copolymers where one block is hydrophobic, the other block is hydrophilic. The problem that you have is that getting a smooth film is tough because Curtis is soluble in oily solvents. He's a sly, oily individual. And me, I am hydrophilic. I'm soluble in things like water and alcohol. So getting a solvent or even co-solvents such that I can generate smooth films is tough if I already start with copolymers that are hydrophobic and hydrophilic. So I have to get around that barrier. And there's a trick that you can use. Jenny, what would you do? And Jenny would say, I don't know, but I'm cold here. It's really, are you cold? Are you sure? You're all bundled up. Okay? So, the trick is you do magic. And the magic that you do is that initially I'm going to start off with a copolymer that's hydrophobic. I'm going to start off with polystyrene, which is this, and this block here, which is called a polysulketyl methacrylate. Hydrophobic, soluble in nice organic solvents. Spin coat films very nicely. I can spin coat films down to a nanometer or less. And then I'm going to take this copolymer, this thin film, and I'm going to place it in trifluoroacetic acid. Now what trifluoroacetic acid does, it's a vapor. All right, so we expose it to this acid vapor, and I can convert the polysulketyl methacrylate to a polyglycerol methacrylate. This is hydrophobic. So I've taken hydrophobic, made it hydrophilic. I've removed acetone, right? And also the trifluoric acetic acid. Acetone, incidentally, has another advantage, is that it's a good solvent or plasticizer for polystyrene. So I can impart mobility into the system. If I look at the contact angle, this is polysulketyl methacrylate, and this is the polyglycerol methacrylate. So this is hydrophobic, has a relatively high contact angle with water. Low contact angle with water, it's hydrophilic. And so what we want to do is we want to take this polystyrene sulketyl methacrylate, and I want to take this and I want to cast a film in the disordered state when chi-n, segmental interaction molecular weight, is below this critical value. All right? So the system is mixed. So Curtis and I are sort of entwined with each other. I'm not going to show you that up here or later. Don't you get the ideas, Curtis. And then I'm going to expose the film to trifluoroacetic acid. And I'm going to make this polysulketyl methacrylate block a polyglycerol methacrylate block. And then all of a sudden, we who are intermixed find out we hate each other, and then we want to separate. We haven't changed molecular weights. And so what that allows me to do is to cast a film, a thin film, a nice uniform film, and then be able to convert the system. So I start off initially, these happen to be scattering profiles, but I start off initially with the film being in this disordered state. I expose it to the trifluoroacetic acid, and I push it into the phase-separated state. Just by doing this chemical magic or trick, I start off initially with scattering profiles that are very diffuse, and that's characteristic of a phase-mixed copolymer. Expose it to the trifluoroacetic acid, and I now start to develop these sharp reflections. And that tells me I've gone from the disordered state into the ordered state. Now, even you could answer this question. Now, I want you to think of a nice day in New Jersey, and you're walking by a gas station. And you walk by a gas station that just happened to be a little rain. And then you see these oil slicks on the water, right? And you look at the water, and what you see is a rainbow of colors. In fact, what you see are colors that you have this variation in color of these oil slick on a surface. Those variations in color are variations in film thickness that are nanometers in size. You have this very thin film on the surface. Light comes in from the top, is reflected off the oil, penetrates into the water-oil interface, is reflected again, and you get color that are characteristic of the film thickness. All right? It's an interference color. You see it every day at gas stations, etc. The thing is that you have very incredible resolution, even though you don't know it, because you get multiple reflections off the surface and the path length is large. So that I can take a copolymer film and I can cast a film on a surface, and this happens to be a disordered film, and now I'm going to expose the film to trifluoroacetic acid, or I'm going to, if this happens to be a phase-separated copolymer, I'm going to heat it, and then what happens is that all of a sudden, you see now, you no longer have these nice gradual changes in color, which tells you the film thickness changes gradually, but rather what happens is that you start to see these very discrete changes in color. You have step changes in color. And each of these step changes in color corresponds to one period or one pitch of the copolymer. This is remarkable. With your eye, you're getting resolution that's 10 nanometers or better. All right? That's pretty good. No electron microscope, nothing. This is just using a simple optical microscope. Doesn't have to be high power resolution. You see different colors that correspond to different thicknesses, etc. So it just so happens that the reason you get these step changes is that with the copolymer, you're forming these layered structures, and the thickness at any point is defined in terms of the pitch or the period of the copolymer. It's very simple. If I take the polystyrene polysulketyl methacrylate and I cast a film, and this film happens to be, it's about 15 nanometers in thickness, I undergo this conversion to the hydrophobic hydrophilic to the polyglycerol methacrylate. And with scanning probe microscopy, this happens to be a height image. This is a phase image. Phase image, nothing, you don't see much contrast. And the reason is that you have polystyrene on the surface. If I look at the height image, you see these very distinct changes in the height. And these height changes correspond to 4.2 nanometers. And that tells us that the distance from the center of one domain to the center of another domain, the pitch, is 4 nanometers. That's the smallest anyone has seen with these types of materials. That corresponds to roughly about 30 DVDs on a quarter, all right, if we can really get the resolution and the lateral ordering that we think we can. And if you look at the domain spacing as a function of the degree of polymerization, this happens to be the polystyrene polyglycerol methacrylate as a function of molecular weight. This is where we're at right now, and we're at a pitch of now around 4 nanometers. And that's great. That's marvelous. Because I'm doing this now in the solid state, and now I can actually utilize the fact that I can use something like acetone, all right, to plasticize the polystyrene to be able to induce the lateral ordering. And I'm going to finish off with one last little trick. And the last little trick that you can use with these materials is that this happens to be a film where you cast the copolymer thin film disordered. And this happens to be a pool of TFA, trifluoroacetic acid. And I now take the film and I just introduce it into the beaker. Okay? I'm wearing gloves, wearing goggles, of course, all of that. Make certain students should do that. All right, and so what that means is that at the base here, I'm closer to the trifluoroacetic acid, so the vapor pressure is much higher. The concentration of TFA is much higher. So at the bottom, I've converted the material to polyglycerol methacrylate. The top, I haven't done anything to it. So I've basically taken a film, and if I look at the bottom, the bottom, it's over here. I've converted the polysulketyl methacrylate to polyglycerol methacrylate, and in the middle, I have some sort of random copolymer. Now, the reason that that's important is that this copolymer here is ordered. This isn't ordered. So I basically go from a point where I have ordered to disordered. And if I were to take this film and leave it there, or drop it down further into the beaker, then what would happen is this ordering front would move up the film. Now, for those of you who have worked in industry or who have worked with silicon or have worked with metals, this is exactly what's called the zone refinement, whereby I can take a front, I can have a film that's ordered over here and disordered, and if I move the ordering front across the film, these structures here I can order and get very good lateral ordering, and further ordering on the film is going to grow epitaxially on what I have already. And so I can take a film and I can just have this ordering front propagate across the surface, and I can do it very slowly. And what that allows you to do is it allows me to use this epitaxial growth to be able to generate perfection laterally in the film. And in fact, these just happen to be results where we basically look at the, this happens to be the bottom of the film, and this is at the top of the film. This is disordered, this is ordered. And effectively what we're able to do then is we're able to take films and we're able to generate structures whereby we have a disordered film on one end, ordered film on the other, and in the middle we have something that's intermediate, but that actually allows us to take this ordering front and to propagate it across the surface. So look, you know, what have I shown you today? Really nothing new, in the sense that we know about copolymers, I know about solvent casting, I know how one can actually reduce the glass transition temperature, etc. But all I've done is I'd be able to take what we know already and sort of mix these together to be able to, one, reduce the size scale of the structures to extraordinarily low values, and also to be able to take and control orientation and lateral ordering. And I strongly feel that by controlling the entropy and the enthalpy of the molecules on the surface, that one is going to be able to generate perfect arrangement of these structures on a surface, and that in turn I think is going to revolutionize the magnetic storage industry, and in fact Seagate is very much interested in what we've been discussing up to this point. So with that, I would like to thank you for your attention, and again I am very honored to be able to present the Marino Xanthos second lecture, I guess, if that's correct. I do want to thank my kind assistants in the front row, and thank you for your attention, and I gladly answer any questions.
Thank you. Thank you, Professor Russell. We have a few minutes for questions. I'd like to finish at 4 so we can enjoy the refreshment upstairs. So please, feel free to ask questions.
So you can make very ordered structures on the surface. Of course, most always may be more than that, because we want to have a predetermined structure. So you have this material, now you want to make a memory. You have to address.
Exactly, but if I can take these structures and if I can make the lateral ordering perfect, all right, then I can bias exactly how the lattice is going to be set up on a surface. Alternatively, this happens to be cylinders normal to a surface. A simpler way of doing this is to give you lines parallel to a surface. So I took these cylinders and flipped the orientation, which is easier to do. Then I have these lines going across the surface, and I can do this over very large areas. I remove one component, and that gives me a line pattern.
So you can address then.
Well, no, see, the point is that now I know this pitch perfectly, and I do this. And so I can make a crosshatch pattern, so I can define exactly where everything is. So it's a soluble issue. The more important thing is that we can generate structures now that industry cannot write to, nor can they address to, because they're too small. And I think what's going to have to happen is that rather than use a simple magnetic head going over a disk, and basically flipping the magnetic domains by writing, I think this is going to have to be done. They're going to have to be flipped electronically, so I can give you a wire array on the surface with these domains interior. So I think that's
right.
Huh?
Type of wiring trying to address.
Yeah, and I think that's what's really necessary to be done, because I think the aerial densities that we can get are far beyond what anyone can use. And I think that current industry technology will be archaic. But that's why industry fights you, though, too, because they don't want to take and throw away everything that they've invested in. So.
Thank you.
Back of the room. Yes.
You know, one of the problems with current technology,
Here.
is the fact that the density is already too high, and there is the power consumption issue when you're doing processing. So basically, in reality, if we're not talking about storage devices, you have to deactivate a significant part of the processor chip, because otherwise it overheats. Is this something that has been brought, to you by people who work in the area?
I'm going to give you my vision. Curtis, how thick is that piece of paper? I hope this isn't important to you. I'm certain it is. How thick? 25 microns. Let's say it's about 25 microns thick, something like that. I can give you these copolymer arrays, porous film normal to a surface. Right? And let me give you domains that are 10 nanometer in diameter, and I can backfill this now with a material that's a good thermoelectric. Some bismuth compound or other, whatever. And I can put electrodes on both surfaces, and now I have a thermoelectric device. Now, with a thermoelectric device, I apply a voltage across it, and the temperature on one side will be lower than the other. Just a simple device. Right? So I have a means by which I can use the copolymers to get heat out. All right? And the thickness of the film is about this. I can then place on top of this arrays of wires, arrays of cylinders normal to a surface, arrays of wires parallel to a surface. I hope I'm not going to... So the entire device is about that thick. All right? I've built in cooling. Now, I'm not saying that's going to solve the cooling problem. All right? The problem that's being raised is that these elements get so small that electrons going through the wires, it creates friction, and that heats. It's a big problem as structures get smaller and smaller. But I think that one can actually build thermoelectric devices, maybe not to solve it, but certainly to help that. So I can give you a storage media with density that's higher than anything you can imagine on something that's about that thick. Isn't that amazing, Jenny? But that's not all. Because I can give you a film now, it's about 25 microns thick, and these wires, I showed you that we can generate wires. We did chromium, but you can do others. And if I were to put now this on an electrode, so I can do this right on, say, a gold electrode, doesn't matter, and then I have another electrode separated from this, and I put a voltage across this, then what happens is that I start to generate, the system tries to complete a circuit, and you get electron buildup at the tip. You increase the voltage, the electron buildup gets higher, 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 and then all of a sudden you start to stream electrons off the tip. That's a field emission device. And if I put a phosphor on top of that, I get light. All right? So I can give you a display now that's about this thick with a resolution that's better than anything that you have now. In fact, I could probably project on the side of a building in high density, a high density image, all right, easily, all right. Fully flexible, all right. Give you storage that's fully flexible, and I have similar ideas about a battery, so I can give you a device that's absolutely incredible. I could sell it to you for $500 and it would only cost me about 10 cents to make. Pretty good. And I'm glad, and you'd probably buy two, which is good. Point is, I can give you, using this sort of very simple technology of taking the copolymers and using the self-assembly process to generate these structures, because it's flexible, because the size scales are so small, because you're using chemistries, which is important, that I can now manipulate and modify the materials. I can generate structures that are ultra dense, flexible, put this, basically take a computer and roll it up on a screen. All right? The biggest problem I'm going to have is my finger, because I have to have some sort of contact with that, and bringing those resolutions to real dimensions is not a trivial thing to do.
The environment is not an issue because the parameters themselves, the characteristics.
When you say, well, look, I can't.
Yeah, the environment, the different parameters may be an issue for polymer, right?
The environment, if, electrically I have I have an insulating material around this, and I can chemically manipulate this to change the dielectric constant. So I can address the dielectric characteristics to some extent. The magnetics is another issue, that this domain, if this domain flips, I may flip this domain, etc. That type of environment, I can't answer that question, but there may be tricks in terms of being able to use combinations of soft, hard, soft magnetic materials, for example, that may help us circumvent that. When we get down to size scales of these that I'm speaking here, there are lots of little things that are going to arise, and I have no question about that at all. But yeah, I'm very excited about the potential that one has to get there. And this is, in a sense, Marino's worked on manufacturing on what I would consider to be a macroscopic to microscopic level, and what we're doing is we're doing engineering now on the nanoscopic level. And so I think, and they're composite materials, etc. So a lot of the things that he was interested in are shown here.
Okay, I think we reached the limit where,
No.
What?
Students must ask one question.
All right.
A student has to answer a question.
You should see fun.
All right, and let's see, I'll give you 5. I'll count to 5, okay? E, R, San, Se, Wu.
You can't win.
1, 2, 3, 4, 5. No one's going to ask a question. Come on, guys. Oh, there it is. Yes, young man. How daring he is. A daring young man.
Yeah, thank you for a great talk. I have a question. There are several block copolymer. What method that you use to synthesize it block copolymer?
Block copolymer, you see, the question you're raising actually is a very important issue in terms of being able to have synthetic strategies that one can produce large amounts of materials cheaply. Up until about 5 to 6 years ago, anionic synthesis was used, high vacuum techniques, and that would never make it industrially. Though right now, actually, a company in Japan is considering the possibility of doing anionic synthesis on a large scale. These materials can be synthesized by living free radical processes. So you can use raft synthesis, you can use ATRP to be able to generate these materials. And that now has taken the cost of producing the materials down dramatically. And that basically has made this effectively a reality. IBM, for example, is now synthesizing large quantities of polystyrene polymethyl methacrylate based upon work of this nature. So it's an important question. If you can't prepare large quantities cheaply, it's not going to cut it. But that can be done now.
Thank you.
Okay. Yeah. I think we have exhausted the time for questions, but I do have a question. So when are you going to get rich?
If I knew that, I'd... Of course, I am rich already.
Of course. I understand
From the
that.
experiences I have had with students, postdocs, and other faculty.
I'm glad to hear this. We all are.
Of course.
Well, thank you very much again for your excellent presentation. And we do have some Christmas present for you. So it is. Let me present you with this. Okay, see if I can wrap it without breaking it. And just hold this.
It's a statue of Marino.
All right, maybe I should have left it there. But anyway, here's the NJIT symbol.
Great.
And this will be followed by actually a real plaque.
To commemorate it.
Thank you again.
Good.
Thank you.